talk will be about the multi-agent modeling of transportation systems and with some recent examples from our lab VT scores. The outline, I'll talk first about the agent-based modeling, what it means and why do we use it and how do we do that. And then intelligent agents and the learning framework that we use to train those agents. I will speak about some applications, including a controller agent and driver behavior agent, vehicle agent, and an example of connected automated vehicle without signals at the end of the talk. And then I'll speak about the implications of not using the learning. And by learning, I mean the reinforcement learning techniques and what really that means, and give some good example about that. So a multi-agent system, what does that mean? And how do we use it? So my work in this field, the way I would summarize it is that there are 5 major components that you need to think about when you are thinking of a system of multi-agents. And there are 3 different levels that are interacting together to effectively implement that technique. So at the bottom level over here, as you will see, there are different agents presented. And what you see here is a person, that's like a pedestrian, for example. A vehicle could be an agent, a municipality or an agency that makes decisions could be an agent, and a traffic controller could be an agent. And you can expand on that level with different agents in your system. How do we define an agent itself? It is basically an entity that can act, an entity that can perceive the surrounding and act, make decisions, and incorporate the feedback that it receives from that surrounding or environment. The way that I usually describe this in my classes is that depending on the context, you are going to define an agent. So if you are given an analogy, if you are in a room and all you are interested about is when do people start the meeting and when do they end the meeting, then you can define the whole room as an agent. Whereas if you are interested in modeling the interaction between people and the questions they raise and how they make decisions, then you're gonna represent each individual in that room as an agent. So basically you think of the context, the scope, and you think about the decision making, the homogeneous decision making, and you surround that as an agent or an encapsulated agent. So at the bottom level, you think about all the agents you have in the system, depending on the context, and you define them. And then in the middle layer, that's the system layer. That's where the interaction among those agents happen. And depending on that interaction, then you think about the top layer here, and that's where you define your goals and your metrics. So your performance measures are going to be defined in that layer over here, and you think about how those measures are close to your goals or your objectives. And if they are far from your objective and you want to make them close to the objectives, then you're going to do one of two things. You will do optimization if these agents are going to listen to you. So if you are dealing with traffic controllers, for example, and controllers are going to do exactly what you tell them to do, then you can optimize the system so that you can reach your objective. If they're not going to necessarily listen to you like people, then you're going to do incentivization. You're going to incentivize them to nudge their behavior so that your goals are achieved. And if you're doing incentivization, then you're thinking about the different game theoretical approaches that are going to happen in there, and the Nash equilibrium and all those kinds of things. So that's, in a nutshell, the framework for the multi-agent system. But then when you're thinking about a multi-agent system in general, like I said, there are 5 elements that are typically incorporated. The first two elements are easy and everyone is thinking about naturally, and those are the space and time. So in a transportation network, of course, you're going to have a space, and then you have, as time passes, different agents are going to be different, moving differently in your network. The third element is the variation. And the variation is basically the trajectory of vehicles and pedestrians and things that move in your network. They are going to move with a certain variation, so with the speed and with acceleration and even the jerk, if you incorporate that differentiation as well. And that's where you could, if you have a homogeneous system, you could be dealing with a system of differential equations or partial differential equations. But not all of the time that you have a homogeneous system, of course, and that there comes the impact of the communication. So a vehicle that is moving and approaching a traffic signal, for example, is going to communicate with the traffic signal. So you could be doing that through the traditional framework of having detectors on the road, sending occupancy and count to the traffic signal, and people in the car receiving a signal display and responding to it. Or you could have connected automated vehicles and things of that sort. If you have buses on the network, you have transit bus priority. If you have emergency vehicle, you have signal preemption. So these sort of communications are going to be happening in your network as well. And the fifth element then is the state machine. That's a little bit beyond what the profession is doing now, even though some of the researchers are doing this, but they are naming it with different acronyms and different implementation frameworks. But I will describe that as we go through the presentation. And basically, in the state machine, you have the state transitions. So you will have Markov chains, and then you have the learning aspect, and then you have reinforcement learning. And if you have a lot of data coming in, then you have big data analytics and those kinds of things. So to summarize, you have space, you have time, you have variation, you have communication, and you have the state machine. These are the 5 elements. And I'll give examples of those as we go through with a different kind of implementation of some of the work that we have done. So when you think about learning, then in this framework, the common questions that arise are, can we predict a condition or a behavior and response from a wealth of data? Can we model and interpret an evolving behavior? And can we generalize the behavior in a state action framework? The typical question that comes to mind again in this era of state machines and machine learning and reinforcement learning, I'm going to show examples of those. How it started at the VT scores. About 11 years ago or so, we had a project, an exploratory and advanced research project with the FHWA. And the project was about the use of the naturalistic driving data and how we can maybe come up with new techniques or new frameworks to analyze the data beyond what was currently the state of the practice at the time. And I like watching movies, so if you have caught on that in the previous 3-layer multi-agent system, you would see Agent Smith sitting there as the pedestrian, and you would see the architect sitting on top over there. So I was influenced by the Matrix movie. I love the Matrix movie. And I give it as a homework to my students in the first class usually. So the idea came about the use of the agents that are going to only be activated when needed. If you look at the figure in front of you, on the picture here, you see the varying traffic behavior maneuvers, vehicles driving in extreme weather conditions where they are slipping and some crazy driving behaviors that you might see sometimes, and so on. And these are not typically captured in any simulation models unless we are doing agent-based modeling in them. But at the time, there was a lot of data like this collected by VTTI, Virginia Tech Transportation Institute, and by University of Michigan Institute as well, through what they call the naturalistic driving data. And in naturalistic driving data, you basically have cameras looking at the road, and you have sensors in the car. You're collecting the speed, you're collecting the acceleration, you have a radar in front of the car with those equipped vehicles that keep recording all the time. Naturalistic data started by providing a selected set of drivers with instrumented vehicles for a year, and they asked them just to drive, and all the data was collected. So there was a wealth of data recorded at the time. What we did with the project is not to collect anymore. The data was already there. And by the way, of course, after that, there was a SHARP 2 project that expanded on this and collected even more data. Our role came after that, is basically saying that, we can collect or extract data from the naturalistic driving data. So here you see the example of a variation, right? You have the distance, and you have the speed, and then you can extract trajectories. And then the idea of training agents, individual agents for every individual driver. So take a driver data, particular driver data, and train an agent to mimic that driver exactly. Not doing the right thing, but just doing the exact thing that the driver is doing, so emulating the driver. And then to take that code, that encapsulated behavior code, and put it in VISSIM through API, so that VISSIM could produce now this kind of behavior and close the loop on that. That was the idea of the project. And then you see a state machine over here. And in general, the description is, if you look at your system, any agent that you're thinking about, you can define different states for the agent, and the probability of either remaining on a state or moving to a different state based on the data. So you can, I'll give a simple example. If I look at a traffic signal, then I could have, for a certain approach, then I could have two states defined, green or red. And of course, if the signal goes from green to red, then it will pass through a constant period of transitioning, yellow and or red. So if I have the data collected from the field, I can quickly find out how many seconds the signal is stayed in green and how many seconds it is stayed in red. And then a probability of either staying in green or going into red will be defined from the data, will be extracted and modeled that way. But there is a policy also that interferes with the state transition here. And the policy is basically defined as, if you are in a given state, what is the action that you are going to take? And to give an example, again, a very simplified example related to the signal, if my policy was just implement a fixed time signal where the signal is 50-50, either green or red, then the state probability transition is going to be defined based on that. But if I implement a new policy and say that for the next 15 minutes, I want this road to stay red, I'm just closing the road for 15 minutes, and I'm doing the analysis for any period within that 15 minutes, then my system is going to stay in state red, and it's not going to transition to state green. So the policy is going to impact the state probability. But at the same time, if you know the state probability, then you can come up with an optimal policy to meet one of your objectives. Could be reducing delay or maximizing throughput. or if you are dealing with safety, maybe reducing the probability of crashes and so on. So the fact that the state transition affect the identification of optimal policy, and at the same time the optimal policy or whatever policy you have is going to affect the state transitioning, is resulting in the need of using artificial intelligence or reinforcement learning, and Bellman equation solving and those kind of things. But then to do that effectively, what we found out is that if you are using reinforcement learning, a certain technique in reinforcement learning that I'm going to present when I get to that point, then you can really capture the behavior of individual humans, and then you can take that behavior and put it in VISSIM to do your analysis. So as I mentioned, you could do machine learning, Q learning if you have fixed states, and one of the examples I'll show is traffic controller is dealing with discrete states, so you can do Q learning effectively. And reinforcement learning in general, if you have continuous state representation, like in driving maneuvers, you're going to have continuous acceleration values, and you have continuous speed values. They're not discrete, because it could take any value. So in that case, you need to adjust your computation and your framework accordingly. All right, so Q learning. In general, reinforcement learning, or a simplified case of it, is Q learning. You have an agent, and an agent is going to sense the environment. So from the environment, the agent is going to know which state it is in. Then it will make an action. It takes an action. That action is going to be perceived by the environment or affecting the environment. And then two things happen over here. The environment is going to transition into the next state. And it also going to give back a reward to the agent. A reward that the agent is going to associate with both the state that it was in and the action that it took. And so depending on that reward, the agent is going to adjust its policy. And I know undoubtedly some of you are doing these sorts of things, but for the benefit of those who are not doing it, to give a very simple example of that, traditional example that is used in this case is that if you are modeling a child who sees a hot cup of coffee and has two options, either touch it or leave it alone. And if the action was touch it, then the cup of coffee could respond back, or the environment in general would respond back by that heat transfer to the child. And so the reward is going to be a negative reward, is going to be pain. And then the next state that is going to be presented could be simply that the cup of coffee is spilled now, so it is even no longer in the vicinity of the child, or it could still be there. But then the child, of course, is going to learn from that, maybe not to touch a hot cup of coffee anymore. So there is a way to represent this in equations. Of course, you have the existing state. We represent them by Q values, and Q values is basically a number assigned to the combination of the state and the action. There is a learning rate associated with the changes, so that you're not modifying the system suddenly, you are modifying the system in a gradually. And then the reward that the agent receives, and all the possible rewards that could happen, or all the possible new states that could happen because of that action, are represented in this equation and are used with the learning rate to update the next state value, the Q value associated with the next state. And again, there is a table that I'll show you in a little bit that gives an example of that. But basically, in a nutshell, what is happening here is that you are having a Q table, and with values associated with all the different combinations of states and action. And then through learning, you are updating all those Q values. And then an agent at any point in time before it takes an action will basically do a lookup at the state that it is in now and all the Q values associated with the different actions it could take, and it will pick the action that has the highest Q value. And then it will do that action, the system continues, and all these Q values are updated again, and so on and so forth. So this way, the agent learns in time. But again, before I go from that, the idea here, or the problem with this idea here, is that I said the Q values of all the different combinations of state and actions. So if you have a continuous space, or if you have many states and many actions, you can have a case of dimensionality issue with the Q learning stuff. So one of the applications for that is dilemma zone. And dilemma zone could be dealt with in two different ways, or actually should be dealt with with two different components. The first one is the controller that is making a decision. So if you have a smart controller, then the controller could try to minimize or eliminate the dilemma zone problem. And also you have humans who are dealing with the dilemma zone problem, and they could learn as well. And I'll show quick examples of the two methods over here dealing with dilemma zone. And again, just to make sure that everyone is on the same page, dilemma zone happens when the driver approaches the traffic signal and the signal turns yellow. And if the driver is very close to the signal, he or she is going to just continue. And if they are far from the signal, they're going to stop. And then in between the far and near, there is that dilemma zone, and where drivers might go and might stop. And if the person in front of you decide to stop, but you decide to go, then it's going to be a rear end crash, and that's why it's a safety problem. So we collected data. Of course, you always have to collect data so that you can use the data to train your agent, and then you take your agent into the simulation package. So an example here of to stop or not to stop, that is the question. I'll show you the quick video, and this is from a driving simulator that, again, we took the data from the driving simulator, and then we took that and trained our agents. So the driver goes on, they see the yellow, and now the question is to stop or not to stop. That is the question. In this particular example, we wanted to use the data also for the human learning aspect, and this work was done with my student at the time, Sahar Hanipur. She's now a professor, assistant professor. And basically the point from this was we wanted to see if drivers who are making a certain decision in dilemma zone, and if they realize that they made a mistake, are they going to regret that decision? Are they going to adjust their decision in the future? So we designed, in this case, the driving simulator itself as an agent, in the sense that the driving simulator is sensing what the driver is trying to do, and based on it, it acts differently so that we can collect the data in a most effective and efficient way, because we didn't want to do a lot of driving simulator studies. That would be infeasible. So in this case, if the driver decides to stop, what we do is the agent here, the driving simulator, extends the yellow so long, tries to entice that driver next time to see if they're going to change their behavior, thinking that, well, we could have passed if we did that without any penalty. But if they decide to go, regardless of what speed they are caught in red light running, and so they have this perception that now they made something wrong, and we want to see if they're going to change their behavior. And then that data, then we train the agents, our agents. Now these are going to be drivers' agents, and we look at the memory structure in humans, and the semantic memory, procedural memory, and episodic memory. And the idea here is that different behaviors in the humans is going to depend on their memory of what they remember, how to do the right things, and also whether they are going to forget after a while. So the idea here is, if you get a ticket today, maybe tomorrow you're not going to do the same behavior. But how about a month from today? Is the memory decay going to have an impact on you coming back to your old ways of driving rather than what you have learned in your semantic memory when you dealt with the situation and you did an action and you received some Q values back to either reinforce or give you a penalty for that action. So this part here is just intended to show you that you could go into that level of details to train your agents. But the idea then is, regardless of how you train the agent, once you have an agent, that agent is following some rules, then you can take those rules and put them in a driving simulator like VISSIM to mimic the behavior of the drivers in that case. In terms of controller agent, you could teach the agent to change its policy so that it can reduce the number of vehicles in dilemma zone. And this work is with Taylor Lee and Zane Adam, my former, again, PhD students, and Taylor now is also a professor in Texas there, and did a great work on this. So the idea here is that you have a minimum green, and after the minimum green, you have the extended green, the variable green. And a controller could be monitoring the state, looking through a radar, like Wavetronics, for example, or any comparable system, could be looking at all the vehicles that are in the vicinity of the signal. And depending on their speed and their location, it could calculate, again, with a variation, how long it will take them to reach the signal. And then the literature saying that if it takes you between 2 seconds to 5.5 seconds to reach the signal, if you see the yellow at that during that period of time, then you're going to be in your dilemma zone. So the controller could scan all of these vehicles in front of it, upstream of the signal, and count how many of them are in dilemma zone. So let's say at a certain time there are 3, then 3, then 2, 2, 3, 2, and so on. And the controller is not willing to take any of these as a good time to end the signal because it is searching for 0 vehicles in dilemma zone. But then if it keeps doing that, it might reach a point where there is a max out, the max timer for the green to continue, and it ends at that time because it cannot continue anymore and might catch more vehicles in dilemma zone. Then you can train the controller as an agent dealing with the environment in this case, and the action that it took was either to extend the green or end the green, and then the number of vehicles that were eventually caught at the end of the cycle as being the penalty or the negative reward. And then you can train the agent then to change its behavior based on this. So in that case, the way to think about it is, if I want to use agent-based modeling here, or intelligent agents, then I need to know what is the state variable. The state variable would be the total number of vehicles in dilemma zone. What are the agent actions? Well, it's either end the green or extend the green. What is the reward? It's the vehicle caught in dilemma zone. That's a negative reward. And then the Q learning parameter that we use in this example was a learning rate of 0.01 and a discount rate of 0.5. And that's then what I said earlier, that you can define your Q values. So for every state and for every action that you could take, you have all these Q values. They are equal in the beginning. There could be 0. And then as time goes by and training happens, you will see how those Q values are changing. So it's really like a lookup table at the end for the agent to see where it is and determine the action that maximizes the Q value. And that is going to give you a policy at the end of the day. So you end up with a policy like this, depending on the number of vehicles in dilemma zone and depending on the traffic volume. There is a simple policy that was defined at the end. If you are having 0 vehicles in dilemma zone, then you always end, but you can get better than that. If you are having 1 vehicle in dilemma zone, in this example here, then up to 600 vehicles per hour you need to extend. But if your volume is higher than that, then you should end, because chances are you're not going to get anything better than that. This figure here shows the comparison between the performance of our reinforcement learning agents and the DCS system that I was part of its development when I was at TPI with Jim Palmerson and his team. And then you see that in low traffic conditions, they are basically almost doing the same. But when the volume gets high, then the reinforcement learning agent behaves better or does a better job, simply because it adapts to the condition, whereas the DCS is always looking for constant values. So of course, it's not going to do as well in high volumes. So I'll take you back now to the high state dimensionality when you're dealing with driver behavior. And in this case, again, following the same way of thinking and laying things down, you need to know the input. So you have the traffic states and actions. The output is the acceleration and steering. So in this case, we're not just dealing with the car following model, but also the lane changing behavior. And the input variable, since now they could be anywhere because they are continuous variable. When you look at the input being the speed and the difference in speed and difference in range, the delta X and delta V, they could be any value. So we need to discretize them. So we used fuzzy logic and fuzzy sets to discretize them. And that was the work of one of my former students, Linson Chong, and others, Brian Higgs and others. Then we have continuous actions that are generated from discrete actions, and we use all the safety critical events from the naturalistic driving data. So here we came up with the safety and mobility agent-based reinforcement learning traffic simulation add-on model, or SMART SAM. And this is the general framework. So you have a neural network, and it has the inputs. You have labels here, antecedent labels. It's basically, that's where the fuzzy set is represented, because if you have the speed as an input, then we look at the minimum value of the speed we found in the database and the maximum speed. And at any point in time when you receive a new input, you're basically looking at the relationship between that input and the minimum and maximum and use that in your training. So this way you could deal with any continuous data. And then you have rules over here, and the major thing that makes this actually work, I think the key point is actor-critic reinforcement learning technique. So you have an actor, which is basically you're training your neural network with a fuzzy set to come up with the value. But then you have a critic over here that evaluate that value you come up with. And this is a way to incorporate, so it looks at the state value basically. And what that means is it's a way to incorporate an evaluation of the state that you're going to end up being in, not just your action. So normal neural network is just going to tell you how close you are in your output to the training output. But with the actor critic, that's not just the case. We are looking at your action is going to take you to a particular state. That state that you are taken into might be so bad that it is going to affect all your future actions. So in that case, you're trying to avoid that state. And that's really a key issue. And if I give any advice about how to do your modeling in a better way than using just neural network, I would say that's the framework that you would want to use. And to give a layman analogy, it's like playing a game of chess. It's not about the next move that you take. It's about the series of moves that you take to make you reach your goal of winning the chess game at the end. So I'll go through this part quickly. for testing and cross-validation, we wanted to test the heterogeneity of drivers. So we take the training from certain agents, we look at their behavior and expanding it, and we do the validation with different data from a different agent and see if there is heterogeneity or if we can represent all the agents with the same data. So that's what you see. That's a key. These are key figures actually. So we take agent A with certain event A, and over here you have time and you have acceleration. So this the blue dots are data coming from the naturalistic driving, and this agent basically was going with a constant acceleration, so zero acceleration, so constant speed, and they went down in acceleration, so they decelerated and then accelerated back quickly and then continued. Whereas if you look at the lateral action estimation, that's the yaw angle, so you're looking at the steering wheel, and that particular agent steered to the right, to the left, and did some erratic behavior going all the way to the left, all the way to the right, until he came back to the center line of the lane and continued. So I would guess that there was a deer, and the agent might have been trying to miss that deer, judging by the fact that the agent continued, and then the deer, I hopefully survived. I don't know the exact state or the exact event, but this is what we see. So basically, the driver was trying to avoid something, and they succeeded in doing it. And then the green line is showing you the agent model behavior. So we were coming really close, actually mimicking that behavior. The same agent with another event, and you'll see how the agent is mimicking the naturalistic driving very closely. You take another driver, same thing, it's very well. Now you take the driver, its own behavior is doing well, but then when you do the driver rules from certain driver, but change it to use the behavior from another agent, you are going to see that the agent is going to follow the trend, but is not capturing the exact value. So yes, goes down, comes back up again, doing that change left and right, and eventually end up here. So the heterogeneity was clear, and then there is heterogeneous behavior. And then the mega agent idea was, what if we take all the data from different drivers and put them together to train this mega agent? How is it going to behave? And then that mega agent, as driver B, is actually capturing most of the changes. And a table shows you the R-squared values for the comparison of mega agent to the cross-validation results. So if you have agent A trying to mimic data from event associated with the same agent, a very high R-square, 0.98, 0.967, for doing it with a different event from a different drivers, yeah, 0.8 to 1.6, not too low, but not as high. And with agent B, the same thing, it can capture its own behavior very well, but with other agents, behavior not so much. But if you do a mega agent, then you are having really good R-squares in capturing all the behavior. So the lesson that you get from this is basically you are not missing the behavior of the agent by bringing in data from different people into the training. The reinforcement learning can actually capture the behavior of multi-agents together. And now with deep reinforcement learning, that could even be more true. So I'll show you now the VISSIM demo. Like, how does this look like? If you get the driver trained, and this is a very simple demo, but I wanted to show a certain behavior. If you take all these agents that are trained now to do this sort of crashes now, because they're mimicking the actual driver from the naturalistic driving data. So we are using the external driver model in this case, and going in, and that's the trained agent code. You put it there, pressing OK. So now we define the agent to follow our rule. Then when you run that simulation, again, this is simple, but just to show the example, this is a normal car going. The car in red means that's our agent. You see that it's not driving in the center line. And then it can actually hit the car in front of it. So it's no longer the inherently safe behavior that is in normal car following models. I also want to show that, so we have the code now, you can change the time to predict that a certain accident could happen, and also the stall duration after the accident happened. And again, simple example, 8 seconds, just to show what that would look like. And now you're going to see something different. So the car in the front is just a normal car. There is going to be a blue car. Well, it changed already. Blue car means normal behavior, Wiedemann model. Red is an agent. Now it had an accident. It is going to stall for a while, and then it's going to become blue, returning back to Wiedemann model. So why is that good or important? Because then you can incorporate the safety and the mobility together. And that's why we call it a smart SAM. So if you have accidents, once they happen, they stall for a certain duration. When there is traffic behind them, you're going to start building congestion and see the impact of that. For the CV-AV application, in a nutshell, and this is work with Milos Mladonovic, who is now assistant professor in Aalto University. We were looking at the idea of getting rid of traffic signals altogether and having the agents communicate and having reservation matrix defined. And the merit of the project was actually for social justice. The idea that different drivers have different intentions, and if you are going to a hospital, maybe we should give you more priority than if you are going to shopping or if you are just doing sightseeing. And then there is a lot of work related to this, and for the sake of time, I'll just go into the implementation of it. And what's important is that with the reservation matrix and trajectory adjustment, you can have agents go through a signal without having a traffic signal in there. So just go through the intersection. And the way is we define the intersection into different tiles, and depending on the vehicle movement, it is going to make reservation for the tiles that it will only use. If it's going through, then it only reserves those tiles. If it is turning left, then it first of all is going to be in a different lane, and then it's going to turn left, so it's going to reserve some tiles going up. When another vehicle comes in, it will only look at those tiles it will use, and if some of them are already occupied, then it will, the central agent will tell this vehicle that you're going to have to delay your arrival by a certain time. And then the vehicle, knowing that, well, it cannot continue the same trajectory, it needs to, let's say, delay it for 5 more seconds, it will calculate how to make that delay by decelerating and accelerating back so that it will arrive just later by that amount of time. And in doing this, it can adjust that trajectory to minimize the fuel consumption and emission. So you can have multiple objectives achieved this way. There is also the idea of revoking reservation. Having different priority assigned to different vehicles means the vehicle with high priority is not even going to see the reservation matrix for lower priority vehicles. But the lower priority ones are going to see it. So let's say this vehicle made its priorities known, and based on that, it received a certain reservation. Then a more important vehicle comes by. This could be an emergency vehicle. It could be a vehicle with a higher priority because the driver is going to the hospital, for example. It's going to revoke the reservation of this vehicle because it doesn't even see it. And it is going to reserve based on that. So it will only make reservation adjustment based on vehicles with the same priority or higher priorities. But now the central agent is going to tell this vehicle that your priority has been revoked, your reservation has been revoked, and now you need to make another one. So it will make another reservation, and this time will be delayed more, of course. And that process continues. If the vehicle reaches this point, then it will automatically receive a highest priority possible so that it will never be revoked again for safety purposes, because maybe this is the last point after which it cannot make safe stop. And then you see that implementation in VISSIM, and basically all these gold colored are mean that they are gold. They got the reservations, and they can continue moving on without stopping. But then how does it feel to be if you were inside the vehicle? So you are following this vehicle now, and you are looking at the intersection approaching the vehicle got gold. That means the vehicle in front of you got reservation. By this time, you got your reservation as well. And then as you approach the signal, you will see how it feels. And of course, there are parameters that we set up in terms of the buffer between you and the person in front of you and the person behind you in terms of tiles. So over here, the buffer was small, but then you see that, okay, you make it through, but very closely to others. Now, the idea is if you are dealing with pedestrians, because they are agents as well, they can interact with such a system with smart apps or smartphones. But in that case, you would want to give them large buffers so that you don't want to scare them. And this will just show you that for some certain experimentation, if agents are approaching the signal with low priority, they come together to fit into a gap. But if they are, these are the ones with high priority. The ones with lower priority are spreading around to find potential gaps to fit into. And that was not programmed, that was an output. So that's the third layer, the top layer in my multi-agent presentation earlier. So it will show you that you can define the rules at the agent level, but then the emergent system and the evolution of the system could be caught at the upper layer where you are looking at what the outcomes are. We're coming to the end. I just want to show you here, as I mentioned earlier, what if we don't incorporate learning? And the anecdote of this was at the end of the project, I was playing with the same data, just using statistical analysis. This is from JUMP. And I was thinking, let me just do this in normal regression analysis and see how bad an R-square I can get, just to feel good about it, right? And my first surprise was, for that data, I got very high R-square in regression analysis, higher even than what we got with the reinforcement learning. So I was devastated. I thought like, so we wasted time. We didn't, we didn't get better than what the simple regression analysis was doing. I was very curious about it, and then looked at what the actual parameter estimates are. And they found that what this is saying is that the next acceleration value is 0.9935 of the previous acceleration value, meaning that once the agent starts, or the driver in this case, that it is trying to model, start to stop, it will continue until it stops. So it leads to the wrong conclusion. Because if you remember previously, when that driver, again, the naturalistic data, the blue dots, started to stop, it didn't stop. It went to a certain point and came back and recovered. So it actually, at the end of the day, remember the chess game, at the end of the day, the driver continues, and the agent-based modeling would actually show you that the driver does continue. Regression analysis would show you total, complete, wrong results. Why is that the case? Of course, it's not a generalization. It's not that regression is always going to give you something wrong. But you see that inflection point over here. It is just one data point. And if you're doing regression in cases like this, it is very easy to just ignore the effect of that one point, because it's just one point. You're still going to get very high R squares. But if you're doing the technique that I just showed in the presentation, that inflection point is really important and it's going to be captured, because the reinforcement learning technique is not just looking at that particular action, but what are all the future states that follow that particular action. So at the conclusion then, what we have showed here and the system that we currently use, it can model the interaction between existing and emerging technologies. In that sense, we can extract and predict behavior of individual elements from big data, from naturalistic driving data. It could be in real time, so that makes it really big data. We can model and interpret system evolving behavior, which allows better management and control. As I said, I'm inspired by the Matrix movie, and ask you all to watch it if you haven't. And they take a scene from that movie that, at the end is, I don't know the future. I didn't come here to tell you how this is going to end. I came here to tell you how it is going to begin. For us, it's continuous beginnings, and with all the evolution, with machine learning techniques and deep learning and big data and so on and so forth, and all the challenges. And welcome to the new norm now in the transportation system. I think multi-agent system is the way to go, and it should be done with existing software, not just a new software. So you could use VISSIM and other software to do that as well. Thank you. This is the end of my presentation.